Huh? Yep. Okay, so we left off talking about monosaccharides, and so now we're going to shift over and talk about disaccharides. And I know some people had questions about how to make cyclic structures and things like that. We'll get more practice doing that because in order to draw the disaccharides, we'll have to make more cyclic structures with the monosaccharides. And so we'll just kind of do it there. And then if other people have questions, feel free to stop me and ask. So what is a disaccharide? It's simply two monosaccharides linked by a glycosidic, there's a new word, bond. Now, it's only new to us in that biologists want to call a glycosidic bond something different than what we might call it. We're simply going to realize that it's an ether bond. And so we should expect to see someplace in that molecule COC, connecting the two parts together. And we're even going to go one step further. They call it a glycosidic reaction. Ooh. But what we're going to call a glycosidic reaction, you guys will learn to recognize as minus H2O, which really means it's just a dehydration. So there are new words, glycosidic bonds, reactions, things like that, but they're the same old things that we've been talking about. Just have to link up the two things. Think glycosidic ether. The reaction is a dehydration. There are three common disaccharides that we'll talk about. And so we'll talk about maltose, lactose, and sucrose. So the first one is maltose. You want me to go back for a second? It's Wednesday. Get that coffee in your system so we're cruising along, folks. Nope, you're done with this week on Friday. So, maltose, or sometimes it's called malt sugar, is obtained from starch via a hydrolysis reaction. What is hydrolysis? Yeah. So what we're going to find is that we put things together. Oops, I'm sorry, that should be plus H2O. We put things together with dehydration reactions. We take things apart with hydrolysis reactions. Those will be the two single most important reactions going forward in these chapters. Don't get me wrong, there are other examples of that, but that's kind of the primary one. And it's made from, or it's made by, combining two glucose molecules together by a alpha 1,4 glycosidic bond. So remember, glycosidic bond just means ether. This 1,4 stuff is just telling us what carbons are connected together. And then what does alpha, do you guys remember from yesterday what alpha and beta mean? Beta up, down, alpha. Buddha stood for. So if the OH group is up on that carbon, we called it a beta, right? And if the OH was down, we called that an alpha. And what was that carbon? We had a special name for it. It's the carbon capable of mutarotation. Does that ring a bell? And it's the hemiacetal carbon. So let's start with glucose then. And actually, I'll probably have to go rifle through my cheat sheet to find it just to make sure I get it right. Usually I don't do the second set of this, but we will do it for fun and profit. Okay, maybe just fun. I don't think there's any profit in doing it. So glucose has a bunch of OHs on the right side. It's got one OH on the left, an OH here, and of course it's a six-membered ring, right? Or six carbons long. And if we number it, because we want to be able to keep track of things, we just start at the top and go 1, 2, 3, 4, 5, and carbon number 6. And do you guys remember what carbons reacted in order to make this occur? So how did we take glucose and make a ring structure? So this part is review. We took the aldehyde group on the number 1 carbon and we bent that molecule around to react with the OH on the number 5 carbon. And so we know that an aldehyde plus an alcohol gives us a hemiacetal, right? And so when we rotated that around, what we ended up with was a ring structure, a 6-membered ring that looked like this, where this is our number 1 carbon. Our number 2 carbon is the OH up or down? Well, what we said is we can think about it as falling like a tree to make this reaction occur. And so this is the number 2 OH. If it's on the right-hand side of the molecule, it's going to be drawn down in the 6-membered ring. The third one then has to be drawn up. The fourth one has to be drawn down. Now, the fifth one is this carbon right here, right? That's our number 5 carbon. If we kind of go through and we number 1, 2, 3, 4, here's number 5. This is the OH from the number 5 one. So notice how I'm making that bond a lot bigger, right? That's where that OH was. And so the number 6 carbon is always facing up in a diisomer. So this is always up in a diisomer. And since in class I got rid of, I'm pretty sure, you guys can check, but I got rid of all the examples where you have to draw L isomers, I'm pretty sure. And so you will always have that CH2OH group up. And then this is that carbon where the new OH group is being formed, and that can be formed up or down. We're going to draw it down so that we have the alpha anomer. And so remember that one, and I'm going to draw it, can be up or down, right? Can be up or down. So remember, when you're taking a molecule and you're making a ring structure, go ahead and make that 6-membered ring. That's the same for almost all of them. There are a few examples of 5-membered rings. We're not going to worry about those. Realize that you always have an oxygen here on one corner of the ring, and you always number it 1, 2, 3, 4, 5, 6. And whether the OH is on the left or the right, or I like to think about it if you take a tree and you just go timber, where the OHs would be pointing down after you go timber, that's where the OHs are going to be on the picture. And if the OH is pointing up after you go timber and the molecule falls over, then those ones are going to be facing up. So maybe we'll say timber. Okay, I'm just not that excited to give me a good timber. So the question, of course, is, if a glucose molecule falls in the forest, does it make a noise? Okay, so this is what we would call alpha D glucose. And notice we throw that alpha in front to indicate that it is the alpha anomer, meaning that that OH group is drawn facing down. Now, what else does alpha mean? And what else does alpha mean? That's what Owen said. Means proportional to, right? And it also means optical rotation, right? So alpha is used an awful lot. And so you have to know what it means in context for a question, right? Sometimes I think we should just invent some more letters or something because we keep reusing ones and it gets confusing. Okay, so maltose then, so we've had our review, is a glucose molecule plus a glucose. And we're going to, of course, remove H2O and make maltose. And so I've got to draw a bunch of glucose molecules. And this is tedious, but that's okay. Life is tedious. So there's my CH2OH. Now I want this one to be alpha. This is OH, down, up, down. And then I'm going to draw a second glucose molecule. I should also note, this reaction is going to, well, I guess I can draw it either side to side or up and down. I usually tend to draw these sometimes up and down just because it's easier to see where everything goes. Let's see, I got an OH, an OH, and an OH. And this one over here is capable, remember, of being either up or down. So here's my plus, and then we'll go down like this, minus H2O. Now here's where it can get, I won't say a little tricky, but you know, if you don't know the answer beforehand, I don't know if you can answer this question very well. Which OHs make the bond? There's a shit ton of OHs on this molecule, right? Remember, when we're looking for water in a dehydration reaction, we're looking for all those OHs, right? Well, there's a lot of them. And so that's where, you know, we said that this makes an, alpha, getting the dashes in the wrong spot, alpha 1,4 glycosidic bond. And you can make other combinations of glucose. You can make it have a beta bond. You can make it have all sorts of bonds. And so one of the things that's amazing to me about carbohydrates is literally the number of molecules that you can stitch together and the different ways that you can stitch them together is huge. And so when we find that the body only uses a few of them, or that a few of them have the right structure and geometry to have interesting properties, I think that's kind of neat. It's kind of like saying you got a lot of Legos, you can stick the Legos together in a lot of ways, but only a couple ways actually are useful, right? So alpha 1,4 means on the first one I'm choosing the number 1 carbon. The alpha part is telling me that that number 1 carbon, that OH group is pointing down, so I guess maybe I should draw the little alpha pointing to the OH. And then what carbon on the other one is it picking on? Yeah, 1, 2, 3, 4. Now, whether this OH is up or down depends on whether it's glucose or some other molecule, right? So the first OH, the OHs on the number 1 carbons have a choice, right? Everyone else does not have a choice. And so here's my OH, and it doesn't matter, I'm going to rewrite this as HO just to make it easier to circle the H. There's my water. And it doesn't matter which one you consider losing the OH and which one the H, you get the exact same product. And so to draw a disaccharide then, we just take 2 monosaccharides and we link them together by that glycosidic bond. Ugh, getting ugly here looking. Definitely getting ugly looking. Let's see, OH down, up, down, up, down. And there's my alpha 1,4 glycosidic bond. And so because this is alpha, this is given the shorthand name of alpha maltose. You can, of course, make beta maltose too if you want. And like I said, you can, since there's, what, 5 OH groups per molecule, I don't know, what, 5 and 5, I don't know how many different combinations that is. I imagine you can draw at least 25 different combinations, right? And that's only with just 2 glucoses. Remember, there's other isomers of glucose that can be used for doing these sorts of things. And then this is given the official name. So everyone calls it maltose. It's just like in real life, you know, every drug you go and buy on the shelf has a common name. because if you wrote the IUPAC name, it would get big, ugly, and no one would remember what it is to buy. So you should kind of be able to understand what the parts of this mean. But I don't necessarily expect you, pyranosyl, to necessarily be able to name them. Although, I have to be honest, there's absolutely no reason why that couldn't show up on a test. So maybe it is worth noting. Glucopyranose. So let's take that apart. This alpha is talking about the orientation of that original, right? D-glucose is simply telling me what sugar I have. The term pyranosyl, well, pyranose means a six-membered ring. And what does a YL ending mean? Yeah, they're kind of saying it's the side chain, that the one on the right is the main molecule and one of them is on the other molecule. And really what it does is it simply differentiates which one should be drawn on the left and which one should be drawn on the right. The 1,4 is telling me about my glycosidic bond, saying take the number 1 carbon on one and the number 4 carbon on the other. This alpha is talking about the OH on the second one. And then pyranose simply means, again, a six-membered ring. I should also, I have a note in my book, page 742, of course, has a picture that's probably better looking than mine, but I don't know if it's any better or worse, really. We do want to point out one feature of the new molecule, and really we should have drawn it for the monomers too. This carbon right here is a hemiacetal, right? Meaning it's got an OH, an O, a carbon, and we don't draw the little hydrogen there, but there's a hydrogen there, right? This carbon here is also a hemiacetal. But in our new molecule, this carbon becomes an acetal. Ugh, that green is okay, I guess. Looks nicer on my screen. But this one stays a hemiacetal. And the reason we want to kind of keep that importance there is that acetals are pretty non-reactive. Meaning that once we make that bond to make maltose, it doesn't break that easily. But hemiacetals are fairly reactive. And that hemiacetal carbon is the one that we said was capable of that term muta rotation, which means that that ring opens and closes. And so what you really get is you get an interconversion between the alpha and the beta anomers. Meaning that when I say that this is alpha maltose, well, if that ring opens up and when it recloses, this OH here is, able to form in the up position, then we just made beta maltose. And so alpha and beta maltose interconvert. Just like, for instance, if you just have the free form of glucose, you're going to have a mixture of alpha glucose and beta glucose. Now your body says, I'm only going to use the alpha one, and so, through a series of chemical reactions, everything we make tends to be with the alpha anomer, but the beta one exists, and we'll see that in some cases it too is used, but for a different purpose. Okay, that's a lot, right? So what do I expect you to be able to do? Draw ring structures, tell me if it's alpha or beta, point out hemiacetals and acetals, do a dehydration reaction between the appropriate parts if told that it's an alpha 1,4, and be able to look at that picture and tell me what sort of bond forms between those two molecules. So a lot of what I'm asking is recognition and the ability to do things with it. So that, if you're reading something and it says, oh, cellulose is connected by a beta 1,4 glycosidic bond, you understand what beta 1,4 means, and you know at some point that it's different from an alpha and that might have significant impacts on how it reacts or how it functions in the body or something like that. Okay, so that's our first one. Our second one, ooh, let's get rid of the green. I don't like it. Let's see, here, how about purple-ish? Is lactose. I wish they had a really bright purple color. This is more like kind of dark red or something weird color. So lactose is found in milk and milk products. It is essentially beta D-galactose plus alpha D-glucose and minus H2O, and the reaction occurs in this case between the, since it's the beta version, it's a beta 1,4 glycosidic bond. And so if we were to draw this molecule, and I'm not going to draw the whole reaction because we can kind of see what happens, I have to first start off drawing galactose. And so actually what I want you guys to do real quick is you've got your cheat sheet with you, right? That has those molecules on it, right? Pull it out, or maybe I'll be nice and I'll go look it up on my version too and put it up on the overhead. But let's practice drawing the six-membered ring so that you guys kind of understand what's going on. So let's see, galactose looks like this. And double bond O, and it's got an OH here, a ho, 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 Merry Christmas. And then glucose I'll draw up here just to keep it out of the way. That's the one from the previous page. That's OH, 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 HO, right? Hey, wow, I might actually memorize this after 10 years of teaching. Maybe not. Maybe just for the week. I'll probably forget everything over spring break. Excuse me. So let's see. You know, these are such a pain in the butt to draw. I thought about getting those little plastic stencil type things and then like using them for lecture and then giving them out for people in class to use too so that everyone could draw lovely six-membered rings. But we don't grade on beauty, we grade on correctness of the structure. So the parts that never change is this part right here, right? That's going to be the same for every single molecule, right? And then if I want to draw beta D-galactose, what is this? What orientation does that first OH have to be? Yeah, it has to point up. Now, where does this OH then point? Up or down? Because that's this one right here, right? And then the next two are pointing up. And then if I draw, ugly, but that's okay. If I draw my glucose, again, the part that doesn't change is that part of the six-membered ring. That's always going to be the same. That's standard. Now, if you look at another website or you look at other pictures that people draw, some people will draw them differently. This is what I would say is the most consistent one I've seen. Most people draw them in this manner. That's an oxygen. So this corner is always an oxygen. That's actually that aldehyde oxygen, right? And then since this is alpha D-glucose, this one has to point down, right? And for glucose, it's down, up, down. And so when we're making this reaction then, we're taking this and this to get our water, right? And then I guess, what the heck, we might as well just draw it out separately. We'll try this blue color and see if this looks pretty. Which OH? Because there's an awful lot of them there, Aaron.
Because I always thought like the right side of the right side of the structure
that's really the number one carbon up here. This one here, if it's on the right-hand side, it has to point down. If it's on the left-hand side, for these two, they point up. This is the number 5 carbon, that's this one right here. That OH is always going to be pointing in this direction to make that 6-membered ring. And then that always causes the CH2OH group to point up. You can actually flip the picture around. You can actually point the CH2OH group down and kind of swap the way things are drawn. Like I said, I'd say 80 to 90% of the time on the internet, I see them drawn this way, and it's drawn that way in your book, so it seems to make sense to do it that way. Realize, though, that some websites, depending on what they're trying to show, might draw it slightly differently. Just like, for instance, notice how I have this bond going up here and down and then up, right? Depending upon what book you look at, they'll sometimes draw them offset like this, or offset like this, or level and then do zigzags. Meaning, how this part is drawn is going to vary. So what you have to look at is, this is connected down, right? And that's connected up, so that must be beta. And of course, this one's down simply because that's down in glucose, right?
Now, all the rest of the OHs, you just copy from the picture up above. So OH, 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 OH. So if I take a look at just that part, for instance, because this goes up and the other one goes down, sometimes they'll show them offset like that. See, that's still pointing down, so they'll draw them in different ways in different books. I try to tend to just draw them level because to me that makes, that's just the most consistent, and sometimes ahead of time I don't know whether one should be up or above. Plus, if they're level, they take up the least amount of room in my notes. So, if I were to name this, what would I name this? So, starting on the left, that's a beta-D galactopuranosyl. What? So this structure here on the left, yeah, you get this from the cheat sheet. You know that it's, and so you know that this is lactose because you got it. Yeah, you don't have to memorize the starting structure for anything. You do have to know how to put it together, how to make ring structures and things like that, but memorizing the structure of galactose and glucose and stuff, I guess really there's only 3 of them you would have to memorize, so I suppose I could make you do it, but since I don't want to do it, you won't have to do it. I think that's fair. So beta-D galactopuranosyl, and then it's a, it's a 1,4 glycosidic bond, and then the second molecule is alpha-D glucopyranose. And so notice, there's the YL ending that's different. The rest of it, though, comes from, looking at the picture and pulling out the parts. The betas, the alphas. We always know it's D-glucose or D-galactose because we only use the D isomers, right? We don't use L isomers in the body. Is it possible to make an L isomer and to connect them together? Sure. It just doesn't happen. I think it'd be interesting if we found life on another planet that instead of like the L isomers or the D isomers, they use the L isomers. Or, one of the things that they talked about, and I can't remember what molecule it was, they found some like bacteria living in like an acidic lake, isolated somewhere, and they were thinking that they might actually not have been derived on Earth because they were looking at how I think it actually used the the D isomer of amino acids instead of the L isomer in a couple cases, and so they were saying that that might have evolved somewhere else. And then of course a bunch of people said, no, that's bullshit. It's just as likely to have evolved here. Okay, so that's lactose. The last one is sucrose. I don't know, I'm tired of that color already. Let's see. Let's do orange. Sucrose. Orange looks ugly too. I kind of like the default blue color. So sucrose
is alpha D glucose plus beta D fructose. And again, it's a minus H2O reaction. And in this case, it forms what's called an alpha beta 1,2 glycosidic bond. And so it seems like it's a little more complicated. Notice that it's not just there's two letters in front. That's because the alpha is talking about the number 1 carbon, and the beta is talking about the number 2 carbon on the fructose. Because the number 2 carbon, if you remember right, fructose makes a 5-membered ring. So this reaction is normally shown top and bottom because there's no real good way to draw it otherwise. And so we're going to draw these kind of going from the top to the bottom. So alpha D glucose should be pretty simple. We've drawn that a number of times. I need the alpha anomer, so I'm pointing that down. Here's my O, CH2OH, OH, OH, OH. And then fructose is a 5-membered ring, so we have to draw kind of a pentagon. And my sides are never the same size. I just hate drawing pentagons. It's almost as bad. It's probably even worse than a hexagon. Whatever. That's as good as it's going to get. So here's an OH, CH2OH, OH, OH. Notice this is also on your cheat sheet. And so my minus H2O, if I grab them, notice I'm taking the alpha 1 from the beta alpha D glucose, but I'm taking the second carbon from the fructose. And so notice that this is the beta and this is alpha. So there's where my water is coming from. And so notice that with the 5-membered rings, 1, 2, 3, 4, 5, 6. We have to be careful how we number that 5-membered ring, or that 6-membered. Okay, it's a 5-membered ring. It's got 6 carbons. And then if we put those together, that again depends on what book you look at, how they draw it. You know, this is an O like this. That's supposed to be a 5-membered ring though. So O. Ugh, ugly. It's just ugly. I don't expect you guys to draw pretty pictures. If you can draw an even halfway decent looking picture, I'm satisfied. How come, which one has which? Two of them. So you're talking right here? Why is there a CH2OH group there? Because that's what fructose looks like. So fructose, if we take a look at it, is slightly different than the other ones we've been looking at in that and I don't know, I have to go look up fructose to see which side the OHs are on. HO, OH, OH. So notice that fructose is a ketone, right? And so when we're making that ring, we're really making the ring between this one and this one. And so what that means is that you've got those two CH2OH groups, the number 1, 1 and the number 6, 1, kind of hanging off the ring.
Why did the OH on the glucose being found
Because I wasn't paying attention. Got to keep Jay honest. Because I was seeing if Aaron was, if people were paying attention, and obviously Aaron is the only one paying attention this morning. Good job, Aaron. No, I just probably was spacing out and going to draw the next thing or do something else and was not paying attention. So one thing that's different about sucrose than the other molecules that we really want to be keeping track of, notice that this is an acetal, right? What's this carbon? It's got an OR, a R group, an R group, and an OR. So what does that make that? So acetal or ketols are like acetals, they're not reactive. So notice sucrose doesn't have a second reactive or a reactive carbon. Notice if we go back and we look at lactose, this is still a, oops, well, okay, it was a hemiacetal here too. And here it's a hemi. And here it's a hemi. And here, I'm sorry, that one gets turned to an acetal. And here it's a hemiacetal. What we're going to find is that if a molecule has a hemiacetal in it, it's going to react different than, for instance, fructose, which has a acetal and a ketol in it. So we want to keep track of which carbons are the hemiacetals and which ones are the acetals and ketols, because that's going to have an impact when we get to talking about chemical reactions. And then if we were to name this, this would be alpha D glucopuranosyl -1,2 beta D fructofuranose. So notice that that ending changes, because what does furanose mean? It's a 5-membered ring, right? Meaning it's got 5 things that form a ring, even if it has 6 carbons in it. So, disaccharides, simply minus H2O reactions. You have to know what the alphas and the betas are all talking about. You have to know how to draw ring structures and to be able to kind of draw these. And the reason I'm going to kind of make you draw them is because if you can draw them, then on a piece of paper, if you see them in someplace else or in some other context, you'll be able to recognize all those parts, right? Because we're able to draw it. Whew, that's a lot. Let's see, where are we at in our homework? Not that this is really relevant, it's so old. We've gotten B done. We've talked about C's, acetals, chemiacetals, mutarotation, all of that stuff. And then we talk about polysaccharides next. Or we can do chemical reactions. I don't really care. It's kind of up to you guys whether you want to do reactions or polysaccharides. Let's do polysaccharides. It's what's next in the list anyway, so what the heck. The only problem is I don't have my pictures out in my slideshow, so I'm slacking. Oops, I'm tired of that color. Let's just go back to our kind of default. Polysaccharides. Notice we are skipping over oligosaccharides. They show up here and there. Your book doesn't talk about them, so I don't see any reason that we're going to talk about them. And we're going to talk about 3 polysaccharides. We're going to talk about starch, cellulose, and glycogen. And then starch is really made up of 2 components. One is called amylose, and one is called amylopectin. Now, what do you need to know for a test? You need to know how they're built, which means you need to know their structure. And then the other thing that we want to be able to do is we want to take a look at how their structure leads to different functions. And so if you know what the different structures are, and you know how they're connected together, and then you know how those different how that generates a different structure, and then why that's important or how that's important. You should also be able to recognize pictures of these drawn in various ways. So as far as the structure goes, they've got one thing in common. And that's the fact that they're all built from D-glucose.
We're talking about all of them, not just
Starch, cellulose, glycogen, amylose, amylopectin, all of that is made from glucose. In fact, notice, every molecule that we've talked about in this chapter, what does it always contain? D-glucose. It turns out that D-glucose is like the standard 4x4 building block in Legos, meaning it's in every Lego structure you ever build. You don't need any of those little specialized Lego structures to build it. People have all these fancy Legos now with the little people and little moving parts and all that crap. Man, when I was a kid, we had 4x4 Legos, and that's basically it. We just had the little 4x4, or actually it's 4x2 blocks, right? They weren't 4x4, they weren't square. And so, D-glucose is the standard Lego. It's the building block of all of these more important molecules. Okay, so let's take a look at starch. You guys already know some stuff about starch. What is it really? Yeah, it's found in plants primarily. Oh, that's right. Who was asking about gluten? Turns out gluten is actually a fat. And that, well, okay, I've got to be careful. It's definitely not a carbohydrate. I'm pretty sure it was a fat, and that it's what's used to kind of act as a binder to hold all the rest of it together. So it gives it its stickiness when you make a cookie or something. And so, like for instance, gluten-free recipes, sometimes you have to add something like xanthan gum to it in order to have the right stickiness to it. So it's found in plants, and it's basically a storage form of glucose. And so it's a way to basically store primarily energy in this case. Meaning plants store that energy, they can then have access to it and run it through metabolism. We, of course, can pick the plant parts and eat them for energy also, and convert the glucose or the starch into glucose, and then the glucose into energy. There's the two types we talked about. There's amylose and there's amylopectin. And most starch is 20% amylose and 80% amylopectin. And they're both alpha D-glucose connected by alpha 1,4 glycosidic bonds. So this is the same on both. What's different is that, well, okay, this is about 250 to 4,000 units long. And so we're talking really big molecules here at this point. If it's got at least 250 glucoses, it can have up to 4,000. What's different about the amylopectin is that every 25 or so, meaning that's an approximation, glucose molecules, there is a alpha 1,6 glycosidic bond. So one tiny little difference, that every 25 or so units, and it varies, one of them is an alpha 1,6 glycosidic bond. And this is what amazes me about kind of chemistry, and also kind of about just in general biology, is that that one tiny little change has a pretty large effect on what it looks like. So what amylose forms is it forms a coiled or helix, or I used to say telephone cord. How many of you guys know what a telephone cord is? Like the old-fashioned ones, not the new iPhone ones that are all straight, right? The ones that are all kind of coiled together. And so what you get is really a structure that looks like this, where it loops back on itself. And so it's not a straight chain. What you'll find is that quite often in a book or something, they'll simply draw it as a straight chain, and when you look at that straight chain, you know, that's the chemical structure, but that doesn't take into account all the bond angles, right? All the tetrahedral bonds in the molecule. And so what really happens is you get this big looping chain of glucose molecules. But if you throw in that alpha-1,6 glycosidic bond, then it's suddenly more of a tree-like structure. And so if we think about, you know, here's a bunch of glucoses strung together. So that line is representing lots of little glucoses strung together, right? And then every once in a while there's a 1,6 bond, and so that causes the chain to kind of break off. And so the chain is continuously branching off to form a big branched structure. So it almost looks like a tree. And so, you know, if this is my main chain, or what we kind of consider the main chain, you know, you can see where every time it branches, that's that alpha-1,6 glycosidic bond causing that. And so it doesn't form nice, neatly shaped helixes, and instead forms that branch structure, or a tree. Okay, some facts about both of them. So this applies to, well, actually here, we'll put it up here. So this applies to starch in general, is that it's easy to hydrolyze. What does hydrolyze mean? It means add plus H2O, and what it really means is it's easy to break apart. One of the reasons it's a nice energy storage form is that it's very easy to simply build it and then break it apart when you need it. And it tends to break apart into what we call dextrin and maltose until finally it's broken apart into glucose. And this whole process starts by an enzyme called amylase, sorry. And you've already talked about this in Todd's class, I think. If it's got an ASE ending, what does that mean? It's an enzyme. And that's not 100% true, but if you do see an ASE ending, that means it's an enzyme. That amylose is found in your saliva. So we really start the chemical reactions, the bioenergetics, that processing of this right away in your mouth as you're chewing. And then another miscellaneous fact is it's about 50% of the average diet, nutritional calories. Which is why I make sure to have potato chips with every meal. It's a food group, potato chips are. Yes, they are, especially Pringles. Who does not like Pringles? Can you think of a single meal where Pringles wouldn't make it better?
Yes, breakfast.
Have you ever tried it?
I've never tried it.
There you go. Okay, the next one is glycogen. And glycogen is kind of what I like to call animal starch. So starch is found in plants, glycogen is found in animals. And it's stored in the liver and in the muscles. And it really is essentially, again, just energy storage. So it's a nice, easy way to package all the glucoses up together so they're just not floating around by themselves, and to stick it there. And what we use it for is we hydrolyze it between meals to maintain our blood sugar levels. I think it's kind of funny, you know, when you take, like, you hear something in one context and then you're able to connect it together with something else in another context. So we all know that diabetics have to worry about their blood sugar levels, right? Or should, right? What I never realized is that they kind of almost literally mean sugar in the blood. I mean, it really is just keeping track of the glucose levels in the blood. And I didn't really make that connection. When I thought about sugar as a kid, I thought, you know, it's that stuff in the jar you get out of the pantry and sprinkle on top of your sugar or your cereal, right? We're not going to talk about it too much, mostly because its structure is basically exactly the same as amylopectin. But, and here, so maybe I shouldn't use the word exactly because I go ahead and use the word but it branches more frequently. And so it has the exact same structure, just more branched. And it branches every, well, one book said 10 to 15 units. I saw another one that said 12 to 18. I never asked stupid questions like that on the book, so either one would be fine as long as you tell me it branches every X number of units or so. I don't care what X is. And so again, it has that branching structure. And so on. So it's not that interesting, meaning we just kind of gloss over it. We know that it's storage. It's basically the animal equivalent of starch. Now, why do animals use glycogen instead of starch? Darn good question. We should Google that at some point. The last one is cellulose. And this turns out to be a structural unit. So it's not energy storage, but it's structure in plants. And it's alpha-D-glucose. Oops, alpha-D-glucose. Connected by beta-1,4 glycosidic bonds. So here's the cool thing. One tiny little change, right? Meaning, if we looked at all the starches, they were connected by mostly alpha-1,4 glycosidic bonds, right? Changing a bond from alpha to beta has a huge effect. Now, structure-wise, this forms sheets instead of coils. And so what happens is if you've got a glucose chain, it forms a sheet that bends back on itself. And so it forms kind of a big plane of material. And remember, there's all those OH groups, right? What do we know about OH groups? So it forms parallel sheets connected by hydrogen bonds. So we're going to learn that hydrogen bonding is one of the actually five forces that lead to, and I'm not talking about the normal intermolecular forces. Those are at play. But of those, hydrogen bonding is probably the most important one for building different structures in your body. So these things are held together by giant sheets of giant sheets held together by hydrogen bonds.
Is it 11 sheets or is that something?
That's the word parallel. Sorry, there's Jay's shorthand for you. It turns out that these are very insoluble, which is strange because normally glucose and those things like that are very soluble. But what happens is these sheets bend all of those OH groups and they form interactions with themselves, and so they're not free to form interactions with water. So they tend to be insoluble and they tend to be very resistant to hydrolysis. And so glucose, easy to put together, easy to break apart. Cellulose, easy to put together, very hard to break apart. And in fact, this is indigestible to humans, right? What can eat cellulose? And more importantly, the bacteria in the guts of, for instance, like termites or cows, etc., right? And that's because they contain an enzyme that breaks beta-1,4 glycosidic bonds that humans lack. Certain part of me says it'd be pretty darn cool if you could somehow figure out how to make humans have the enzyme that breaks down beta-1,4 glycosidic bonds, because then instead of having to go out and plant things and things like that, we could just be like cows and horses and just go and graze. Mow the lawn, bag it up, and there's dinner. Now, I have to admit, grass doesn't sound terribly appetizing. You sound like you've tried it. Yeah, it really would be kind of a different kind of salad. I don't know. I was thinking about this last night, knowing that I had to lecture on it. Actually, I was thinking about it in the shower. See, my shower times are kind of weird sometimes. I just start thinking about what I'm going to lecture on or something like that. And I was just, thinking along the lines of, it'd be interesting if you could figure if you took grass and instead of, going through the cow, you decided to skip that step, just have a vat full of the enzyme that breaks down the 1,4 beta glycosidic bonds and then just remade it into potatoes or various other things. So that's what Jay thinks about when he's taking a shower, assuming he's even awake enough to think in the shower. Depends on the morning. So, tiny little change from alpha-1,4 glycosidic bonds being coils, being good for energy storage, being easy to break. We have an enzyme to break it down. Starch tastes pretty good because it's French fries basically and potato chips and good stuff like that. Change it to a beta-1,4 glycosidic bond. We no longer have nice little coils. We have these big sheets, and they're held together by hydrogen bonds, and they're very resistant to the hydrolysis, and we lack the enzyme to dissolve those. So just a tiny little difference between a alpha-1,4 glycosidic bond and a beta-1,4 glycosidic bond can do it. Now, what I want you to do in your book, since I didn't put these in my lecture, is go look at the pictures. Ask yourself, could I tell starch from, say, cellulose? Meaning, can I tell the difference between an alpha-1,4 glycosidic bond and a beta-1,4 glycosidic bond? Or could I recognize amylose, amylopectin, for instance, or any one of those, meaning, oops, not beta, can I tell what an alpha-1,6 bond looks like? So there's some recognition that you guys need to go through for that. So, due on Friday. Even though Jay's not here, you should be slipping it under his door so that you're not falling behind. We'll say, what are we on? Chapter 27, C and D. So A and B were due today, C and D due tomorrow, or Friday. That's okay. Then, okay, you can turn it in tomorrow. You can turn it in a day late. Although some people are beginning to stretch my patience with how late things are. And things are going to start being a zero. I'm not looking at anyone in particular, okay? Yeah, that's still not a good excuse.